So thank you very much, and good afternoon, everyone. Today I want to talk to you about the recycling of polyolefins and flexibles and the solvent-based recycling processes. So at first I will give you a quick introduction into what the Fraunhofer IVV is and what we do, and then I will come to the solvent-based recycling of polymers. After that, I will explain a little bit about the urgency of the recycling of packaging materials and state-of-the-art recycling. And then I will come to projects tackling the issue of packaging recycling with the solvent-based recycling process. And to round that up, I give a brief overview on the EU regulations and draw my conclusions in the end. So the Fraunhofer Gesellschaft is the largest organization for applied researchers in Europe, with about 30,000 employees in 76 institutes and research units all over Germany. And the Fraunhofer Institute for Process Engineering and Packaging, short IVV, is located in Freising in the southern part of Bavaria. We do research in many different business fields, ranging from food to packaging, process and machinery, but also recycling and environment. And this is where the department where I'm working in is located, the process development for polymer recycling. What do we do there? We focus on the recycling of plastic and metal plastic composites. And for that, we have developed and licensed a solvent-based recycling process, the so-called Creasolve process. With this process, we are able to recycle a target polymer from a waste mixture or composite materials. And during the process, we are also able to eliminate contaminants and odors. And we engineer this process up to the commercial scale. And next to that, we also do the objective evaluation, optimization of plastic recycling plants and processes, including the technical and economic evaluation of the processes, but also the product evaluation and the optimization of the recyclate to increase the revenues. And in the end, we also do a qualification for a certified and efficient recyclate production. Our department is separated into 3 different working groups. One is focusing on the recycling of packaging materials, especially multi-layer packagings, which is currently very challenging. And for that, we have delamination processes, but also selective extraction technologies. Another group is focusing on the decontamination of plastic wastes to eliminate the contaminants in the polymer matrix, for example, legacy additives, to obtain recyclate in the end, which is in compliance with statutory provisions. And if we want to upscale such a process, we have another working group for that, they give advice and assistance in the construction of recycling plants that use the Creasolve process, and they also customize each recycling process to the specific waste stream to increase the efficiency. But what exactly is solvent-based recycling? So at this slide you can see a comparison of the different most common recycling technologies. One of the most common one is still incineration, where you just burn your plastic waste and obtain a little bit of energy from it, but also greenhouse gases are emitted. And then there is chemical recycling, where you decompose your polymer to monomers or feedstock materials. But the most favored one should be material recycling, because in this recycling technology you don't need to polymerize the monomers again, but the polymer chain stays intact. And the most common one is currently the mechanical recycling, but this requires a high purity of the waste stream you want to recycle. We focus at our institute also on the solvent-based recycling. Here you physically dissolve the polymer from the mixture, and it also stays intact as in mechanical recycling. So the polymer chain itself remains untouched. And how does it work? When we have, for example, a waste, we can selectively extract the target polymer. So the target polymer goes into the solution and is fluid in this state. And then we can clean the solution and purify it from contaminants which are dissolved or undissolved. After that, we can precipitate the polymer and dry it to obtain a free product a product which is free of foreign polymers and impurities and harmful substances and has qualities competitive to virgin material. During the drying, we also recover our solvent, which can be reused for the dissolution of the target polymer again. So the solvent is always used in a circle. This process is applicable for all thermoplastics, and we use only specific and safe solvents with a high boiling point. When we obtain a new waste, we first start the process development at lab scale. There we choose the solvents and the processing parameters. Then we can further upscale it to our small technical plant, where we can produce 5 to 10 kilograms per day in stainless steel equipment. And after that, we can also even further upscale it to industrial demonstration scale, where we can produce 100 to 1,000 kilograms of sample. And we've already implied 2 industrial demonstration plants. One is operated by Unilever in Indonesia. I will tell you more about this plant later. And one is currently going into commission for the recycling of polystyrene insulations and decontaminating the harmful flame retardants which were used in insulating materials. So the solvent-based recycling process can be applied to very different waste streams, and today I want to focus on the packaging materials. And in packaging, there are mostly polyolefins used, but also PET for the PET bottles. But you've heard a lot about the PET recycling in the previous presentation, so I will focus on the recycling of polyolefins. But why is it necessary that we need new technologies? So the current recycling rates are quite low. About 18 million tons of post-consumer plastic packaging waste is collected, was collected in 2020. And 10 million of that were collected separately, so in a packaging waste stream, but 8 million tons were separated in a mixed waste collection. And if it's mixed with other household waste, then it's not very likely that it will be recycled at all. So the first step is that the packaging needs to be collected separately. And if you now look at the number and the recycling rate of 46%, you may think, hey, we are close to the PPWR targets, which are set for 2025 and 2030. But the 46% are calculated with the old calculation method, which takes everything into account which goes into a recycling plant, but not what comes out as a recyclate from the recycling plant. So if you look at the recycling rate, which is calculated with the new method, which takes everything into account which enters the last compounding step, the recycling rate is far lower, so only 32%. And if you then have a further and more detailed look into what goes actually back into packaging materials, the rate is only 8%. So we currently have a very limited loop in the plastic packaging market. And the same applies for the polyolefin recycling. As you can see, most of the collected packaging is going to energy recovery or landfill, and only a small percentage of that is recycled. So about 17% of polyolefin packaging ends up as recycled polyolefins for different applications, and only 6% of all collected polyolefin packaging ends up as packaging material in the end. So why are the recycling rates so low? And I will explain that with the state-of-the-art polyolefin recycling. So at first, you need to collect your waste stream. And then your material needs to be sorted. To the left, you see a scheme of a very modern sorting plant. And currently, the easiest method to separate the polyolefin films or flexibles is by classification. So everything which is a big foil can be easily separated, for example, by wind shifting. wind shifting. And then you have the films, which are mostly of polyolefins and mostly of polyethylene, and they can be recycled in some plants. But a high-value recyclate can mostly be obtained only when you really separately collect the PE foils, for example, by front of store sorting. Because if it's in a household waste stream, then it already has a lower quality. And yeah. And after you've sorted these films, you can grind them, wash them, and dry them. And after that, you can extrude them, so you can also have a melt filtration applied, where you further separate impurities, and then you convert it into new materials and applications. And not all of the polyolefins can be separated in the PE film fraction. Others are lost in the mixed plastic film fraction, for example, the multilayers, which are currently most times burned and not recycled anymore. So the limits of the state-of-the-art recycling are that we have a lot of multilayer packaging materials which currently cannot be recycled and disturb the mechanical recycling of polyolefins. And monofilm waste fractions are separate in some recycling plants, but the recycled polymers underperform due to intentionally or non-intentionally added substances such as printings, organic contaminations from food, for example, or barrier layers. So it's not very likely that they can be applied to high-value packaging. Furthermore, you have a quality fluctuation because not every waste batch is the same. You also have a polymetric gradation due to the high thermal stress during the extrusion. So what we need is an expansion of the collection, sorting, and recycling of the polyolefins, but also we need new technologies which are required to reach the PPWR targets. And this slide, you can see a comparison of two films which are made of recycled polyethylene. To the left, you can see a mechanically recycled polyethylene film, which was made of shrinking films as an input, so a very, very pure and separately collected waste stream. And you can already see that there are some, or not some, there are a lot of gels inside of the foil, which disturb also the mechanical properties. And this was just one recycling loop with mechanical recycling. And to the left, you can see a film which was recycled with a solvent-based recycling process from a PO flex waste, which is currently only used for energy recovery and not recycled because it contains multi-layers, but also residues of paper and other contaminants. So as you can see, we don't have any gels, or just a very, very few gels in this film. And yes, it looks a little bit grayish, but it's from post-consumer material, which is currently not recycled at all. So we can see that the solvent-based recycling is a good alternative. And now I come to a few projects which we have currently running. One is the cooperation with Unilever, which tackles the problem that multi-layer packagings can currently not be recycled, and an alternative for landfill or incineration was necessary. And we have proven that the recycling of these multi-layers is feasible with the creosote process, and we've already successfully upscaled it into an industrial pilot scale with a capacity of about 3 tons per day. This pilot plant is already in operation for, I think, about 2 to 3 years now. And it proves a circular economy of packaging materials because the recyclates from this plant are already reused in new sachets in Southeast Asia. In another project called Circular Packaging, and we focus on the commercialization of our creosote process in Germany for the recycling of multi-layer and PO flex packagings. And we've already installed a pilot plant, which is in operation with a capacity of about 500 tons per year. And now we are planning to construct a demo scale plant with a capacity of 20,000 tons per year. And we are benefiting now by the integration of industrial partners, so we are closer to the market, and then we also want to have a competitive advantage in the EU with that. And now I come to another project funded by the EU called Multicycle. Here we've also proven that multilayers are recyclable with the Creosote process, next to the recycling of fiber composite materials, which were also part of this project, but I want to focus on the recycling of the multilayers. And we've demonstrated this on a scale of 100 kilograms per day, and we have obtained high quality products from packaging wastes. So we have obtained pure PE, PP, PA and PET fractions with a solvent-based recycling. And how did that work? For example, here we see a post-consumer waste, and we first extracted selectively the polyethylene, and we were able to process the polyethylene with, for example, cast film extrusion, but also blow film extrusion. And this was completely feasible within usual processing parameters, which were also applied for virgin PE. And after we've extracted the PE, we took the residue, and then we extracted selectively the PP. And this was also feasible. And the PP was also processable and even stretchable. So at the very right picture, you can see that a stretched PP film, and you can't see any holes or something like that. So the mechanical properties were very, very good. And in a collaboration with Amcor, we have also shown that we can apply our films and our recyclates in new packaging materials. So the very left packaging, the disinfection wipes, contains recycled polyethylene. The packaging in the middle contains recycled polypropylene, and the very right packaging contains recycled polyamide, which were all recycled at a scale of 100 kilograms per day. So we have proven that we have a technology for the recycling of flexible multilayer packaging, and we can already apply it into foils, co-extrusions, and laminates. But the last step is missing, the application in new food packagings. And this is why the project called Circular Food Pack came to life. This is coordinated by the Fraunhofer IBB with a budget of about 5 million euros. And in this project, we focus on the whole value chain. So at first, the efficient sorting, for example, by establishing new tracers. And then we also want to have efficient recycling of polyethylene with a high purity to reduce the virgin PPE content in flexible laminates. We also give guidelines for a circular design of flexible packaging, and furthermore we determine and compare the ecological footprint of the process cascades, and we also give support by standardization in the food and packaging industry. And in this slide you can see that we have done tests with input coming only from food packaging and input from mixed packaging, and you can already see a difference here. If you have sorted really only food packaging materials, you get a very, very pure product in the end. But if you have a mixed waste stream, which is currently the case, the product doesn't look that good, and you have many contaminants inside. And we want to fix that with a process cascade, including the washing and deodorization, the de-inking and delamination, and the Creosote process, which also includes the purification. And next to the recycling technologies, we also have a look on functional barriers for applications of recyclates and flexibles. I don't go that much into detail because Mr. Langowski will go much more into detail of functional barriers later. What is a functional barrier? It should prevent the migration of admitted substances into the food, and to have an idea which packet or which barriers work the best, we have developed a test method where we first contaminate a polymer by compounding, then extrude the contaminated pellets into films, and then we can laminate the films with functional barriers and do some permeation measurements. So how good the barrier performances of each barrier films are. And just a few examples, there are inorganic barrier layers, there are co-extrusions, and there are also barrier lacquers which can be applied. And in the end, we want to give a guideline for a design of a flexible packaging which comes from recycling, so with a recycled content, and is able to be recycled again. So there we recycle on, there we focus on a monomaterial design with a very high content of polyethylene and a thin inorganic layer as a barrier. And it may also have a de-inkable printing combined with a delamination primer on it, and maybe also a tracer for the efficient sorting of food packaging materials. And in the course of the project, the functional barrier will be selected in accordance with our screening results, and the design for recycling and circularity will also be targeted and investigated to have, in the end, a target of food approval of the technology. So now at my one of my last slides, the legal framework by the EU. The regulation on packaging and packaging waste was already very good explained by Justin, so I don't go that much into detail. Just a few main targets of this legislation. It should reduce the packaging waste. It sets requirements for the packaging in case of design, but also in case of minimum levels of recyclate contents. And next to that, there is a new regulation concerning or regulating the food contact of plastic materials. I think there will be a more detailed discussion tomorrow, so I will just briefly explain that it is enforced since October last year, and it will ensure the safe recycling from waste materials, and that the food application of the recyclates is safe in the end. So in conclusion, currently the recycling rates of polyolefins, but also of all packaging waste, is very, very low. But there are hopes that there are other technologies, for example, the solvent-based recycling technology, which can handle such material and waste streams. And we've already proven that it's feasible with the solvent-based recycling technology on demonstration scale, and are currently upscaling it to the commercial scale. And what we've further proven is that our recyclates are applicable in packaging. And the new EU regulations may enhance the recycling, and enhanced recycling may lead to the application of more recyclates in food packaging materials. So thank you very much for your attention. Are there any questions? In the first row.
Thanks a lot for the. Hello? Yeah, okay. Thanks a lot for the presentation. So it's feasible technically. I just wonder if you already considering some economic, factors. What would be then the difference if you produce this recycled plastic? What would be, from the economic point of view, the price would be much higher than the, it's because that's actually at the end, it's quite important, yeah, how we would deal with this.
No, currently we plan that the our recyclates have approximately the same price of virgin polymers. And for example, with the circular packaging project there. We've done some economic evaluations, and we see that a Creosoft plant using this technology for packaging wastes is approximately economic, beginning with a capacity of 8,000 tons per year. So just as a rule of thumb. Any other questions? Yes.
Hi, I would like to know a little bit more about the tracers that you mentioned. How does that work? And on the other, like, because I just can't imagine. And on the other hand, I would like to ask about and if you have considered the environmental impacts of the solvents that you're using, how are you treating them, or how, like, disposing, or what are you doing with that part?
Okay. First about the tracers. So we don't really focus at the Fraunhofer Institute on the tracers. So the tracers are produced and investigated by another company. So I don't know that much details. Maybe you can come back to, or you can contact me and I will send you the contact for the tracer materials, so they can probably answer your question the best. And concerning the solvents, they can always be recycled. So the treatment is, if you dry the polymer, you obtain the solvent, and then you can condense your solvent, and if it's pure enough, you can already just recycle it, or maybe then there needs to be another distillation step in between. But in most times, you can just recover the solvent as it is from the polymer and reuse it for dissolving again. So there is actually no loss of solvent during the processing. You're welcome.
So I didn't quite hear.
Sorry.
Understood. So you can recycle the mix flexible.
Yes.
And the result is another flexible.
Yeah. So for example, I've shown the post-consumer waste from flexible materials, and we have selectively extracted the polyethylene from that, and we were able to make new flexibles with our recyclate from that.
So, but you have to separate the different flexible polymers, or you can recycle it all together.
And we don't recycle them all together because we can selectively extract only one polymer at a time. So if we have extracted the PE first, then from the residue we can extract the PP, for example, in a second step, and then we could go farther and extract the PET, but after some point it's not economic anymore.
Okay, and the complex flexibles, the package with flexible that is flexible with a mix of materials.
For example, multi-layers.
Yes.
Yes. For example, if you have a PET multi-layer, then we can easily selectively extract the polyethylene from it, and you have the PET fall as a residue. So, for example, we have also done tests on post-industrial material where we have PE and PET multi-layers, and we have selectively extracted the PE and recovered it and processed it to flexibles. And we have also recovered the PET as a residue. And we were also able to process the PET into new fiber materials. So if we have a pure waste stream, we can also use the residues and further process them. Any other questions? No. So thank you very much.